This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Sorry, I turned off the recording, so if anyone that wasn't here, they won't be able to listen to the start of that lecture. You guys can fill them in. So yes, the femoral component's inserted, ball's put on, and then it's complete. So it's relatively not that many steps, but you can see there's a few key parts to it to do with alignment. So this this part here where the femur gets reamed, if that's the cutting tool's a little bit this way, a little bit this way, that's going to change where the femoral component sits. And also this this cut, right? If this cut is taken in a slightly different plane, then where this little notch here, so when you drop it down, where that will sit will be slightly different. So this type, so there's two different types in which the implant's anchored into the bone. So cemented and uncemented or press fit. So cemented is where you use polymethyl methacrylate, so PMMA, generally just called bone cement. And so that gets inserted into the cavity made in the femur, and then the femoral stem gets press fit into that bone cement. The bone cement hardens and locks it into place. The setting time of that bone cement can be adjusted to the surgery, but generally the surgeon's got to work fast and effectively, because if that bone cement hardens before they're ready, that's a bit of a disaster, right? Getting it out is not so easy. And then it also has opportunities to add different different materials to the bone cement to enhance different effects. So they've been putting antibiotics, there's growth factors, all sorts of different things that have been tried, being added to powder. And generally this type of approach, cemented, is used when the bone stock is really low density, so for osteoporosis particularly. So if the bone's really low in density and you try to press fit it, it might break. So this is where you would consider using cemented hip replacement. So this just has a couple pictures showing how they might also, what also needs to be considered with the bone cement. So the bone cement, if you end up with any little holes, like air bubbles inside the bone cement, it's going to be a stress riser, so that's a potential failure location. So you need to get it all the bubbles. So how do you do that? You inject the bone cement under pressure. So that's what these pictures here are sort of showing. So it's to reduce porosity in the bone cement. And then also what's done, because the bone cement's also added to the acetabulum side. So again, if they've got low bone density, you don't want to be press fitting the cut into the acetabulum. So bone cement's added there as well. To help the bone cement get anchored, they also put these little holes in to so the bone cement locks into those little holes. Are there any questions at this point? Anything that I didn't explain very clearly? Clear? Yeah, so these little holes. Yeah, I was just saying, imagine if you put the bone cement in without them, that bone cement may not lock into place, it might spin, right? So the bone cement then has some holes to sort of help it grip. Yeah, obviously, the surgeon, they have to be careful not to drill too deep, because if you go too deep, bone cement will come out the other side of the pelvis, which is a disaster. But look, surgeons do make mistakes. It's one thing that I sort of come to sort of learn through observing these surgeries. They're not perfect and they do make mistakes because they're under a lot of pressure to do these surgeries quickly. And another thing aspect to try and help with the porosity is when the implant gets put in, it needs to be pressed into the bone cement. So that pressure helps with it getting attached, so adhering to the bone between the implant and the cement, and also reducing any air bubbles, so porosity. So preparation of the femur. So I was saying that these brooches typically get used because the thing is the femur has the intramedular cavity, so you don't need to actually drill it out. You can use just these brooches that they're razor sharp, and press them in and they'll cut away all the bone. But then if you're going to be injecting down into that hole where the bone cement goes, you need to have a plug to stop it going too far down the bone. So they have this distal plug that gets put in, and then fill it up with bone cement, pressurize it so it needs to be packed in tight, and then the implant gets pressed in. So as I was saying, the advantages of bone cement allows implants to be joined to porous bone. Antibiotics might be delivered that way. Rapid and secure attachment with prosthesis. So when you press fit it, it might take time for the bone to fuse with the implant. But in this case, once the bone cement hardens, it's locked in position. Disadvantages: the bone cement can degrade over time. Debris where bits break off can cause inflammation, and you can have loosening. And also for engineering, it's actually very challenging to actually try and work with, because what you end up with is 3 different materials. You end up with bone, cement, implant. Even 4 layers. You can have cortical bone, trabecular bone, cement, metal, right? So whenever there's a change in material properties, it becomes very difficult to simulate that and have reliable predictions. So the other option, cementless or press fit, this promotes osseointegration, bone growth into the implant. To promote that osseointegration, the implant will be covered with different types of texture or surface finishes. So some of those are cast, sintered, so we have these little pieces of metal put onto it, grit blasted, or even coated with hydroxyapatite. So all these different treatments put onto the surface of the implant. There's no real consensus on which is best. Every company sort of has their own type that they claim is the best, but we don't really know. It could be that for different individuals, different types of surface finishes would be best, but going to that extent where you're personalising something to a patient, that's not a point that we're at in terms of engineering. So these are, there's so many different types available, and they all have different sort of ideas on how to do it. So you can see generally what they do is only put this this texturing to enhance osseointegration only in this area here. You can see that on most of these, right? So that's in the metaphyseal region of the bone, so up here. Does anyone have any ideas why you would say only do up this region and not the entire bone? Oh, sorry, not the entire implant. So just only texturing for osseointegration here and not, this is a very unusual one, not doing that more commonly. It is, but it's not the primary reason. No. So the main reason is for stress shielding. So if you only have, so say the implant starts up in this region, right, the femoral head, you want to transfer that load as quickly as you can to the bone, right? So it's only texture in this region to have quite close to the femoral head, it transfers the load to the bone. And then all the bone below that is then receiving load. So, in other words, this type of implant will mean that the bone receives load from up here, whereas this type of implant means the bone's only receiving full load from down here. So that's the main reason. And they have all other types of implants that have fins on the side, all to do with its rotational stability, so whether it's going to torque out of position. But sometimes it's preferable to have it where you can actually rotate it, say for alignment, so the surgeon might place it and they can turn it a little bit. Okay, so another question then is, with this type of implant, why then does it even have the bottom part of the implant? Like from here down, why is it even there? If it doesn't actually fuse with the bone, why do they actually put it on there? This region here. To do with practicality, what might that mean? It, kind of. Not so much, actually. It's mainly just when the surgeon goes to put it in, it helps guide it down the canal into the right position. So it's just basically to help guide it, placing it. It doesn't actually receive all that much load once it's all integrated with the bone. Okay, so some of the aspects biomechanical engineers or biomedical engineers need to look at when so the design criteria. So we have surgical constraints. So how to implant, we need to design an implant that the surgeon can actually use. So how will the surgeon take an implant and place it in the body, and how do they align it into the correct position? It needs to be simple, I think I mentioned before. If it's too complex, it makes it very challenging for a surgeon to place in the right position, and it's time consuming to place. If it's time consuming to place, it's more likely things are going to go wrong with placing it. And it needs to be revisable. So if it fails, it needs to be able to be removed. So they're the main surgical considerations. In terms of the implant design, when we design implants, we usually use finite element modelling because the structure of these implants is just too far from ideal to be able to do simple beam bending calculations. So we usually use finite element modelling, Have you guys used finite element modelling already in previous classes or subjects? I hope you do while you're studying here at some point, because it's very much, you know, the go-to tool in industry if you want to analyse load. So finite element models, I think you might not have used it, but you'd be kind of familiar with what it is. It's a computer model of whatever you're analysing, and it predicts the stresses and deformation of the component. So we use finite element modelling to assess whether our implant design is going to work. Typically we assess it for yielding and fatigue. We look at stress shielding. So stress shielding is the implant causing the bone not to receive any load. That's bad. Whether the loads are going to be favourable for enhancing osseointegration, and what the contact stresses are like. So if we're doing a joint replacement, we look at contact stresses, because contact stresses are very predictive of the amount of wear that's going to happen in the implant. So the other point is the design should be able to cope with subject-specific differences and promote stability. So stability is everything. If a joint replacement's not stable, it's not going to be used, right? Because the patient won't be able to work, and it also walk or whatever, won't be able to use it. And it also increases the risk of it failing considerably. So as an example, you have a ball and socket joint, right, like a hip replacement. If it's really unstable, you could end up with the ball grinding against the edge of the cup, and that grinding can cause particles to be sheared off. And that's exactly what happened on the metal-on-metal implant. It was slightly misaligned, it wasn't very stable, you get grinding of the edge. Those little pieces of chromium cobalt went into the body and caused all sorts of nasty things. But another aspect that needs to be considered with implant design is how it's going to be manufactured. Complexity in a design is difficult to machine, and it's if it's difficult, it's time-consuming and it's expensive. So having said that, medical implants are some of the most complex components that are actually machined or manufactured. Surface treatments may be used, and then manufacturing techniques may be used to enhance the mechanical properties. And then you have biocompatibility. So we don't usually look at biocompatibility from our simulations because you don't really know how the body's going to react. So the usual way biocompatibility is assessed is via experiments. So that might be biochemical assays or like sort of biochemical tests. Brooke will probably talk more about these types of things, but say if you have some new material, you would then put it in, say, in a test tube with synovial fluid and just see how it reacts. So tests like that are usually used. Next step up from that, say you have some new material that looks promising, it's not, doesn't seem to be reacting with the environment that would be similar to the body. You then look at animal models. So they actually, if they have a new design, they might go and put it in a rabbit or a sheep or something like that. We worked on with a group that were working on new types of spine replacements, those vertebra replacements, and they were actually putting them in goats to see if they work, because the goats, their head comes round and vertical, whereas a sheep has more of a sort of, you know, it's more oriented horizontally, whereas, yeah, the goat's head sort of comes up like that. So they wanted to have the loads going through the implant to be more similar to human. So you do animal trials, and then if that works, you then go to clinical trials, where you put them on, you know, a group of patients, and hopefully for them it works. Usually for those sorts of patients that volunteer for those trials, they're pretty desperate, as in their quality of life is that bad they're nearly willing to try anything. So how do the surgeons actually align them, an implant, in a surgery? So one approach are these guides. So they'll have a guide, all different sizes for different femoral heads. They'll place that in position, and then you see here there's a little slot. So they have a saw basically. It's like an oscillating saw. They'll go through that slot and cut it. So that this guide is specifically designed for one type of implant. But you can see this part here that's holding the guide. That's the critical part. That needs to be put in the right position. And there's a few different ways they might do that. It might be attached to the bone. So what's not shown here is it might come down and attach to different parts of the bone. Yeah, there's quite a few different ways, but ultimately it's not the most precise way to do it. But it is the way that they do it. I think I said these brooches. Yep, so acetabular cup gets reamed. They've got to be careful not to ream too deep. And when the cup gets placed in here, you could have it different orientations, as in it's a hemisphere, could be a little bit more this way, a little bit more that way. And that's very much just the surgeon's sort of judgment. They'll look at it and say, oh, this looks about right. So overall, it's pretty qualitative, which is not really ideal considering that the joint alignment's critical for how much load goes through the implant. So one way that they're trying to improve upon this is the Mako robot. Has anyone heard of this before? You can just go to YouTube and type in Mako, and you'll see a nice gory video of how these things work. But essentially what it is the robot, you have a robot arm that's holding the cutting tool, and it won't let the surgeon cut the wrong place. So you see these markers, they've basically been used to figure out where the robot arm is and where the bone is. So then the robot, it's the navigation system, the robot will know precisely where you need to be cutting. So then the surgeon can hold this tool and come down and cut it. If they try to cut in the wrong place, the robot doesn't let them. Okay, so the thing is with this is, the way I'm thinking is, well, why do you even need a surgeon at all, right? The next step will be taking the surgeon out of that. You'll always need surgeons to deal with soft tissue, at least for the foreseeable future, because how does a robot know what's soft tissue and what's not? Whereas bones are rigid. If you have a CT of the bone and you attach these markers, see these markers here, they're attached to the bone. The robot effectively knows where the bone is in space. But soft tissue, it's deformed. So if you took an MRI image, that image and then reconstruct the soft tissue, that might move, so you don't really know where that is. So I think the next step from this will be where the surgeon just comes in and cuts the joint all open and then just says to the robot, come and cut, and then the robot will come in and right, cut the bone. So it's a very sophisticated approach to try and tackle this whole problem with alignment, and a very expensive approach. So yeah, they only just started using these. We'll see what happens in the future. Another approach are these 3D printed guides. So you can see these guides that might have your cutting plane. So you might see this cutting guide is sort of a one size fits all, or like 10 sizes fits all approach. But if you can design this guide that's been specifically designed for the patient based on their CTs, then you can improve. So maybe then you can manually put this guide in the right position more reliably. Another approach I've seen is using lasers. I won't go into that. But you can look it up. Optimized ortho. There's a nice video on sort of how it works. Okay, so next up, the surgeon. That's all to do with the surgical alignment. But what about the finite element analysis? So typically we make finite element models from the CT images, and so we take a CT image of the patient, and then we can segment out the bone, and then we can design an implant to go in, right? But that's relatively easy. More challenging part is what loads do you apply to this, right? We don't really know, if some random patient has a scan, what loads are going through their joint. One approach to try and get joint loads is an instrumented hip implant. So a patient had a hip replacement and the implant had strain gauges attached to it, and then effectively became a load cell. So then they directly measured the joint force. So that's one way you can get joint force, but the point is that that's a hip replacement, it's not a native hip. And secondly, that's for a different patient, right? So another way we can get joint forces is via motion capture and modelling. So you'd get a subject to come into a gait lab, we'd put markers all over them, you can see the little dots, have them walk over a force platform, and then we can calculate what the joint loads are. And you can see those blue and red lines are the muscle forces. So you also get muscle force. Another way is cadaveric studies, where you just say you have a cadaver, so a dead person's body parts, and then you put them in this sort of configuration and just press on the joint to say body weight. So that's another way to get it. But ultimately, these three approaches, there's going to be incompatibility. They've been developed from a different person. So you imagine, like, if the loads were applied to me, they're going to be different from everybody else. So that's a limitation that we don't really have a good solution. One approach is just simply to scale the loads to different body weights, but yeah, it's not ideal. So that's how to validate these loads is certainly challenging. Any questions to do with that? Okay. So once we've done our finite element analysis, what would we then look at? So we've got this FE model, we've put in the loads, and then it predicts your stresses and deformation. So you might have stresses that look like this, right? So first of all, we want to make sure it's not going to fail mechanically. So we'll check stresses are below the yield strength for both the implant and the bone. Checking whether a bone's going to fail is tricky because it depends on the bone properties as well, as in the bone density, but it can be done. You need to check for fatigue. So are these stresses, if you assume that a patient's going to experience those stresses, I can't remember how many cycles, but say 25 years worth of loading cycles, will it fail? So we typically design for 25 years lifespan of the implant. Look for stress shielding. So this stress distribution, you can see that it actually is shielding the bone. So this region here, the greater trochanter of the femur, it's not getting any load. So what you would expect to happen is then it will lose its bone density in this region. So that's a problem. If you can do anything about that, it would be good. We want to make the stress state favourable for osseointegration. So compressive loads in the area of the implant that we're trying to fuse. So if say this implant was textured just from here to here,